Right, right. I've hit the button. Can you hear me now? I mean, like, whoever's on the other end. Is my voice working? So streaming to here and drawing should be working. Yeah, fine. So the other interviewer is going to be here in like a few minutes. I'll just get up to let him in. Is the voice okay? Yeah, fine. People join up and then start in 15 minutes or 10 minutes based on interest. People join up and then start in 15 minutes or 10 minutes. Cool. Okay, so let's start. I'm going to teach the first part, which is regarding dynamic connectivity and offline DSU. So first, let us look at the template problem that we are trying to solve. So this is the base problem that we are targeting today. So I hope everybody has heard what DSU is. It's when you have some set of points and you get queries of the type 1, add an edge, or 2, like some property about the currently created component. So like let's say this is like a component. So these will just add, and this is another component. You could have a query that asks, wait a minute, I'm getting call. I guess some delay होगा पर अभी तो आ रही है आपके पास. हाँ मतलब तू एड वगैरह करवा देना. Yes, yes. हाँ तो उसमें नहीं आ रही आवाज. um so मैं अभी देख रहा हूँ स्ट्रीम उसमें तो आवाज आ रही है. हाँ ठीक है मेरे से शुरू कर. या मे बी सॉरी. Yeah. I'm hoping that voice is not an issue. I've called it out there. Okay, fine. And the second type of query could be something asking about, say, the number of components. This problem is the basic solution to this is DSU. We are not going to cover what DSU is because it's a fairly simple algorithm and this is supposed to be a demo lecture. So, what offline DSU tries to solve is a third type of query, which is remove an already added edge. So you could have this edge right here, and I want to remove this off my DSU. How could I do that quickly? So reuse the space. So the first way to do this is to use a technique called square root decomposition. What our goal would be, let's say there are some queries. This is the query list. Each position we have a certain type of query. Let's say the first query is to add an edge. The second query is to question, number of components, and third is to delete some particular edge. So all of these will have some corresponding data. Like this will have some UNV, this will have some UNV, and this will just be tell me what number of components there are. Let us split this array, which we have, into bits of size square root n. So this is currently a 9 plus 2, 11 sized array. Let's break this into pieces of size 4 and try to separately solve for each of these tiny pieces. For any given edge that has been added, say an edge from node I to node J, there would be some position k in array q at which this node was inserted, and there would be some position L at which it was removed. So the lifetime of this edge I comma j was from k to L. Now, if you consider for a particular part in this query array Q, any edge that was inserted before or like removed before or inserted after or removed after can be can need not be considered while computing the answer for this square root Q sized section. So what I mean by that is, say you have a DSU. These edges were these two edges were added before we reached this target position. Let's say this is our start, and this is our end. So edge 1 and edge 2 were added already. Unless edge 1 and edge 2 are being removed between start and end, I do not need to worry about what's going to happen to them. They're not going to be popped out of the DSU. So let me create a separate stack or a separate vector that maintains which edges could actually be affected during my processing of this start to end chunk of my query array. Right. So consider this query array to be something. Okay. Now you have this structure. At each query, we can do one thing. We can evaluate what was the structure before any of these queries appeared. That was what was the state. Um, what was the state of DSU before start, and then we can look at all queries in the stack and process them again. Right. So for this, we need a basic data structure that can undo operations. Let us try to build that data structure first. So I'm going to show you some code. We're going to build something called a rollback DSU. The only job of the data structure would be to undo the latest add edge query. So we would have some new metadata called a history. This would store what was the state of the DSU before any update was done. So usually in Unite, when uniting two components, you have find, you get the parents, and then you update the parents and the sizes of the corresponding components. Now we add a new step in which we save what was the state of the parent, size, and component count metadata just before the query. So in history, I have saved these components, and anytime I need to go back in time, like go back the last 5 queries I did, for example, I would call the rollback snap function. It would evaluate the stack for the past queries until we have reached the time that we need to reach. So how exactly is this working? History is a stack that contains pointers and their values just before the update was done. So this is a int address. It will store the variable as a pointer, right? So if I need to undo some operation, I can just simply set the first of my saved entry as the second, and this is equivalent to moving back in time. So now that we have this rollback DSU as a base component, we can try to see how this evaluate all queries in a stack operation might be possible. Okay. So we have this DSU that has already been made with some parent array up to the start pointer. When you get the next query, let's say an edge from U to V, and you make that update, you would have written into your history stack the previous state, and the previous state was defined by these three bits of information. As soon as you go to the next query, let's say you are at the first query right now, and this is the first query. You move to the second one, you would straight up move this history back. So you would pop from history until the start pointer is reached. So how many pops would we be doing? So we'd be doing approximately root n pops, or rather root q pops, or q is the size of the stack of the query array. And the next time you are asked any query, either of type 1 or 2, you just evaluate all these popped operations again. So you'd be performing another root q inserts into the DSU. So this is the basic idea of how square root decomposition would work while solving offline DSU. In each operation, you would be spending root q time at max, and uh, the number of operations is q. So we get root q, and because path compression cannot be done in offline DSU, uh, like this rollback operation over here would not work if path compression was done. The inserts in this DSU would be log q size, log n size. So this is the final complexity you would get for the square root decomposition method of performing rollback DSU. So this is like the basic idea. To improve this, to get this down to something of the sort of q log n, we have to do something more interesting. So in the queries array, the lifetime of an edge was described by the interval in which it was inserted and then removed. Say this is the insert of I. I was inserted here and I was removed here. If we were to somehow solve all queries inside this segment, we would not have to touch this node. So this is the basic idea through which we are going to build a new data structure. What we are going to do is we are going to build a segment tree over this query array. So let's consider a size 8 query array and build a segment tree. And the last line is trivial. So once we take our node, our queries from the query array, and find the interval for each node, each addition removal interval for each node. So let's say node 1 was added at 1, removed at 5, and again added at 7 and removed at 8. And node 2 was added at 2 and removed at 3 alone. What we will be doing is marking the corresponding nodes that make up these intervals with the node that was added at them. So the node 1 to 5 would correspond to this interval and this interval. So we have a vector here that stores what edges need to be added at this point, and we put push 1 into that vector, and similarly push 1 into this vector. And for 2 to 3, we do the same thing. We push 1 into this vector and 1 into this vector. So if I hope everyone knows how segment trees work, the number of segments that a particular range needs to be broken up into to fit into a segment tree is log n. So in a segment tree, if you do a range query, it takes log n time for it to process. It's the same for the same reason. So now we have this data structure that allows us to process all queries in the node below it by forgetting about what happened at the nodes above it. And as soon as we are done with these queries, as soon as we are done with these queries, we can move out of this node and pop all the entries, all the moves that were done at this node. So basically, you will perform a DFS over this segment tree. You would go down, add the node 1 because you saw the node 1 over here. You'd go down again. Again, if there's a query here, you'll answer it. And when you're coming back up, you will pop all the nodes that were added on the way. So this can easily be maintained with the stack. I hope everybody can understand why this is working. So you'll have a stack going down, and it would just simulate the way that a call stack in recursion works. So as for how this would look, the code for that is here. I would be making so I'd be making 4n nodes in a tree, and each of those nodes would store a vector. This vector says what edge should be added. So the edge could have been any like 1 to 2, 3 to 4, 5 to 6, anything. For each interval LR, I'll perform a segment tree like update at each of the required nodes of the segment tree. I'll push my edge back. So this 4n leaves because that's how you'd initialize a segment tree. You'd go up to update. You'd tell the first position that was added and then the next position that was removed. It would perform a segment tree like update. Now you have this set of edges. You just need to perform a DFS over the segment tree. So while performing the DFS, you want to know what is the point at which you want to roll back to. So you store the current snapshot. Snapshot is just the length of the history array. So the state of our DSU is being defined by the size of the history array at the current moment, right? So you'll put some elements in, the history array will get larger. Then when you want to come back to a different state, you just shorten this array until that length is obtained. So you'd perform the query that is required in the tree. This vector could be empty, and most of these questions will be empty. So I've not proved the time complexity yet. I'll come to that. Then if there is a query of type 2, which is the ask query, we will output the number of components. And this is just code for going to the next child in the segment tree. So this would look quite familiar because this is the same transitions as in a segment tree. Right. And then now that we're done with this node, we need to leave. We need to go back up the tree. So we just roll back until the snapshot that we had stored here. Okay, so let's talk about why this is fast and what the complexity for these operations are. So in the entire array, for a given the number of intervals that you would have. So in this case, you had some these three intervals. The number of intervals would have to be bounded by O of n, or yeah, O of q rather, where q is the number of queries, because each interval is representing one operation. So they cannot be more than a q operation. And there are exactly q operations, so the number of intervals have to be O of q. And the insertion of each interval into our segment tree takes log q time, because it's a segment tree like insertion. So for the preparation of segment tree, we'll be using O of q into log q time. Right. Now the next step is DFS. In DFS, across let's calculate time in two pieces. The first one is for the recursion or for the DFS itself, and the second one is for walking on the vector stored at each edge, or rather at each node. So there would be a vector stored at each of these nodes, right? To store what edge has to be inserted when you enter that node. So we're gonna call those operations as type 2 operations. So the type 1 operation of DFS is quite obviously going to take O of q time, because there's O of q nodes, right? And if you sum up all the elements in all the vectors, so the sum of all elements across all vectors in the segment tree, this would be bounded by the number of queries. So this would also be O of q. So we know there's at most O of q insertion and deletion operations. That would mean that this would take O of q log q to process, giving us a total complexity of O of q plus O of log q, q log q. So we have brought our complexity down from q root q log q to just q log q. So this is the theory. Uh, as a problem to do in this lecture, I'm introducing this problem, extending set of points. I'm gonna let everyone read this problem, and after 10 or 15 minutes, I'll explain how this could be done with dynamic connectivity offline. Okay, I hope everyone's at least given thought to this question. So the first thing to notice is, let's say there's a Cartesian plane. There's some points already on it. So if I add a point, say this point over here, the added nodes, there will be added nodes only if these two, like this connection already doesn't exist. So let's say if I had put this node in already, and these two would be redundant. So a new node would only be created if these two nodes, like for example, aren't connected already in my whatever data structure I maintain on the side. And if this node is in fact new data, then for every node that is at the same y coordinate, and for every node that is on the same x coordinate, I would end up adding one new point each. So let's say if there was some y here, this would get added along with this x here, and it would get added along with this y here, and so on. So what we will do for a given x comma y, that is node that is being added, the number of new points, if there are any new points added, would be equal to how many points are at the same x coordinate. So number of points at the same x coordinate times number of nodes are at the same y coordinate. There's a few nodes here. There's a few nodes here. The addition of this point would create every combination of these two, and so on. So with this hint, I think everybody would find it quite easy. You have a set x, or rather a component for every x coordinate. So x1, 2, 3, 4, 5, so on. And for every y coordinate, we want to keep track of how many nodes are there at a current x and a current y. So this can just be done with some vectors over here. Just keep the size based on added numbers. And each time a query is asked with a particular point, like you will have the sum maintained. So each time a point is added, you just add the product of the corresponding two entries into your answer. As for how this relates to dynamic connectivity, you need some way to add and remove these points. So the addition of some x comma y needs to be handled fast, and the removal of x comma y also needs to be handled fast. So I'm gonna give like 5 more minutes for people to think past this point. So the main observation has been revealed. To convert this into a DSU question is also important. So let's wait for another 5 minutes, and I'll do the rest. Right. So someone asked in chat uh, how these transitive points should be removed. So if you consider like some set of points that are already in the thing, let's say like this previous example, if any x coordinate and y coordinate are connected, let's say this x coordinate and this y coordinate are connected with this point, you would end up creating all these transitive points. So basically, once some x and some y are connected, you can consider all the possibilities to have been handled. So let's say you were to remove this point, everything including this point would be removed. So all you have to do here is to maintain, let's say there's a vertex x, or rather a node x for every x, and there's a node y for every y. Each time a point x comma y is added, you're basically connecting its x coordinate. Let's say its x coordinate was this y coordinate, and seeing if they're already contained in this component. So if some other point had been present in the set, its combination would have made sure that this x and y are in the same component already. But if they are not, you would straight up add this times this to your answer. And when you're deleting, all you need to do is undo this operation, which is the same as a normal DSU undo, because you just keep in your history stack what was the size of all the points before this x comma y was added, and just undo them when needed. So this is just a normal DSU, normal rollback DSU, and you set up the query, I mean the query segment tree with nodes being the x coordinates and y coordinates. You would have to have some metadata which says size of x's, which is basically what is the size of how many numbers have the same x coordinate. So for size of 1, I would store the size x of 1, I would store how many nodes have 1 as their x coordinate, and for size y of 1, I would store how many nodes have y as the same x coordinate. This problem we'll add it to a mashup, and I expect that everyone should be able to solve it. Like it's a code for this problem. You can check the tutorial if you're not clear on the solution. So yeah, that's it for the DSU part. We'll now move to the part for randomized algorithms. This should also be interesting, and there'll be a different lecture for this.
Okay, so I'll be taking up the randomization part, and hopefully you found that offline DSU part interesting. And randomization is also pretty interesting in the case that it's very logical and reduces our uh, casework as well. So let's just start with what is randomization. So randomization is like you can think of it as like using a source of randomness in our algorithm to make it non-deterministic and like still maintaining a very high chance that our algorithm is correct. So basically, we have our algo. Oh, okay, shoot. We have our algo, and we introduce some randomness while still maintaining a very high probability that our algorithm is correct. So let's just start with something pretty basic, which is how to generate random numbers. So one thing that C++ provides is use of rand. So rand, what it basically does is it generates a random number between 0 to rand max. And this rand max, this thing is guaranteed to be greater than equal to 32768. So this random number, rand function generates a random number between 0 to this rand max value. But the thing is, our computers, they are deterministic machines, right? So our computers cannot really generate random numbers. So what internally this rand function does is it takes a starting value x, this is called seed, and we pass it through some functions, some processes, and we get an output. This output, this might seem like it is totally random, but since we have already performed some functions on this particular starting value x, so it depends on x and it is deterministic actually. So if you call this rand function, it initially might seem like what you're getting is totally random, but that's not the case. It's deterministic. So this is deterministic. Okay. So there are actually pretty serious problems with this rand function. First is it only generates 0 to rand max, and this rand max is actually dependent upon implementation and our compiler as well. But in like code forces, this rand max is actually set to be 32768. I told you that it's guaranteed to be greater than equal to 32768, but on code forces, it is actually set to this exact value. So, and one more problem with rand function is that it uses fixed seed. Remember, I taught to you about what our seed is just a few minutes back. So seed is the starting value on which you perform certain functions to get a output. So this seed is actually fixed when you use this rand function. So how is that like harmful? So like if you use this rand function in your solution, so on online judges like code forces, they allow people to hack your solution. So since you are using a fixed seed generator, so they can create a particular test case which is designed for your solution, and it is designed such that your chances of getting a wrong answer are pretty high, or maybe like you end up using too much time and you get a time limit exceeded as well. So this rand function is not really recommended to use. And what we can do instead is use Mercian twister. So there's this random number generating function called Mercian twister that's defined under the random header. So what this basically does is now we are not required to pass a fixed seed to this random function. We can pass a dynamic seed as well. So what dynamic seeding helps us is if you are passing a dynamic seed, your chances of getting solution, your chances of getting hacked are pretty much negligible. So what we do is we pass we use time seeding. So time seeding ensures that your seed is dynamic. This is dynamic now. And now that since our seed is dynamic, our chances that our solution are getting hacked is pretty much impossible. Okay. And yeah, and one more thing is like I'll just talk you about like although there's also a function called random shuffle in C++. So this what it basically does is it like shuffles your array in a random order and yeah in O of n time. But it is also not recommended to use this as well because it uses rand internally. And I think this is already depreciated in C++, but still, yeah, you should know. So instead of this, we use shuffle, which you can pass begin pointer to the array, end pointer to the array, and you can pass this mercy twister function as well. So RNG. So now we have a dynamic seed, and this shuffle is guaranteed to be like very random. Okay. So I think the theory part for this randomization is pretty much very limited, and I think it is best explained by solving a few problems. So I'll just give you a very starting introductory problem sort of. So let's say you have, I'll just write down the question. Let's say you have an array of, let's say length n with values ai. Okay. And you can ask a query of I comma x. What this query basically returns is it returns true if ai is greater than x, otherwise it returns false. Okay. Uh, let's just scroll down, and your task is to find max element. Just scroll down a bit so you able to see max wait, max element of the array within, let's say, something around n plus, let's say, 2000 queries. Okay. And n is, let's say, up to 1000 and AI is, let's say, up to 29. So I'll just explain the question again. What basically this question is, you are given an array of length n, and the values of array can be up to 129, and you have a interactor with which you can interact and ask query of the form I comma x, where if AI is greater than x, it will return true, otherwise it will return false. And you have to find the maximum element of the array within n plus 2000 queries. And constraints on n and AI I've already written. So try to solve this, and yeah, we'll discuss in like probably 5 minutes or 10 minutes maybe. Try solving. What's the time? It's 20 minutes. Okay, let's do 9:15. Okay. Okay, I think everybody should have tried at least till now. Doesn't matter if you got the intended solution or not, but at least you should have tried. So let's just discuss few things that instantly come to our mind when we are seeing this problem for the first time. So one such approach could be like you have array A1, A2, all up till AN, and N is up to 1000, and AI is up to 199. So one such approach which should come to your mind instantly is like performing binary search n times to determine value of every AI, and then you can simply compute which is the maximum and report it. Okay, so you can do this, but since binary search takes log AI times and you are performing this operation n times, so you'll run into something like n log AI solution. And this pretty much is not within our intended number of queries, which is n plus 2000. For large enough n and for large enough AI, this will easily exceed this. So this is sort of like a binary search approach, but it doesn't fit in our query limit. So now what we think is like, let's just try to optimize this solution a little further. Okay. So we have our binary. So let's scroll down. So let's just try to optimize this binary search solution now. So let's say you have A1, A2, A3, A4, all up till AN. And let's say you find A1 using log to 199, which is nearly 30. So let's say you find A1 in 30 queries. And for A2, let's say you just spend one query to check if it is greater than A1. So you just use one query to check if it is greater than A1. If it is not, then already your answer can't get any better. So you just shift to A3. And if it is, sorry, what did I say? If it is greater than A1, yeah. If A2 is let's say less than A1, then your answer can't get any better. So you just shift to A3. And if it is greater than A1, you are forced to perform binary search on this A2 again. Similarly, you do with A3, whatever current maximum you have tracked up till A2. If A3 is less than that, you don't perform binary search. If A3 is more than that, you perform the binary search. You perform binary search. So this, like again, you are spending at least n number of queries to just ask if it is greater than the previous max, and in the worst case, you'll be asking all the n indexes. You'll be performing binary search on all the n indexes. So we have come down to this n plus some sort of n log n as well. So our idea to optimize, like, it is pretty intuitive that you'll just ask if it is greater than the current max that you have tracked. If it is more than that, then only you perform the binary search on this index. And if it is less than that, then there is no need to perform binary search. But in worst case, like if I just set my array to be constantly increasing like 1, 2, 3, 4, 5, then you are forced to perform binary search on every single index. So that will take n plus n log AI time. So that pretty much exceeds our query limit as well. So all these approaches that we have thought of till now, they like exceed our query limit pretty easily. So what we can do is, I'll just scroll down. What we can do is we can try to introduce randomness. So randomness is the key idea. How exactly? So let's just start by shuffling our array in random order. So initially, let's say if our array was something like 1, 2, 3, 4, 5, we'll just random shuffle it to get maybe something like 2, 1, 4, 3, 5. Something like this probably. Okay. So now we have random shuffled array, and and our approach is basically to perform BS, binary search, only if AI is greater than current max, right? And now let's see how our scenario turns out if now that we have a random shuffled array. So let's just define, let's define PI as probability that AI is greater than AJ for all J less than I. Okay, so basically AI is the first occurrence of the prefix max up to I. And if you scroll down, okay, so we have defined PI. Now let's see, since our array is like randomly shuffled, so let's see what our expected number of what do we say, expected number of change in prefix max that we get. Let's try to calculate this value for like 2, 3, 1, 5, 4 for this array. 2 is the biggest here, 3 is the biggest up to this point, 1 is not the biggest, 5 is the biggest up to this prefix, and then 4 is not the biggest. So we have 3 changes here. Let's try to calculate what this value will be for this. Let's calculate what this expected value would be for a random shuffled array. So I'll just so since we have to calculate number of changes in prefix max, I'll just scroll down one here. I'll use something which you are probably familiar with, which is linearity of expectation. Okay, so let's just say that out of the first I elements, whatever be my prefix max, let the first occurrence of that prefix max can be at any of these indexes since my array is randomly shuffled. So it can be at 1 with equal probability, it can be at 2 with equal probability, it can be at 3, and with equal probability, it can be at I. So probability that my prefix max first occurs at I, prefix max up to the ith point, first occurs at index I itself. That probability is basically 1 by I, right? And by using linearity of expectation, we can just see that expected number of changes in my prefix max is basically 1 into P1 plus 1 into P2 plus 1 into P3 all the way up to 1 into Pn. So again, Pi is basically the probability that my prefix max up to the I first occurs at my index I. So expected number of changes is basically by using linearity of expectation, we can say that it is 1 into P1 plus 1 into P2 plus 1 into P3 all the way up to 1 into Pn. And this is basically nothing but sigma 1 by I for I equal to 1 to n, which as you may already know, this is close to natural log of n. Okay, so now you will see the point that what by introducing randomness we have achieved. So earlier in the worst case, we were performing n number of operations. In the worst case, we could perform n number of binary searches. But now, by introducing randomness, the expected number of binary searches that we are going to perform is only limited by natural log of n. So this is the expected number of changes in prefix max. And now if you see like if you see how much time our algorithm takes, or how many queries does our algorithm take, we first query every index to check whether it is greater than previous current, which is if it is greater than the current max that we have tried. So we perform n queries for that. And for natural log of n numbers, we perform the binary search. So natural log of n into log 2 of ai. So we perform these many operations. So this is n plus uh, natural log of n for, let's say, n equal to 1000. I think I told you for n equal to 1000. Let me just check what is the natural log. Okay, and then 1000. Okay, did I say 1000 or what? It was 2e5, right? I think. Okay, I think it was 2e5 or something. Yeah, so where's my first one? So 2e5, yeah. So n natural log of n for 2e5 is close to 30, and log 2 of 1e9 is like nearly 30. So this is n plus 390 queries. In these many queries only, we are able to perform our entire operation. And our limit was n plus 2000. Like even if our solution, even if like the expected number of changes varies a little, it will easily fit in within n plus 2000 with the main 390. So that's how like introducing randomness is helping us to like achieve a correct solution with very high probability without like letting our algorithm become slow or like very complex to code. So that's how randomness helps. This is like pretty useful in many sort of CP problems, and this is not very obvious at some point of time. Like some point you might think like, okay, I need to like probably code a deterministic solution, but maybe like thinking if you can like come up with a randomized solution with which is maybe pretty much easier to code and saves you a lot of time and basically fits within your query limits or whatever the constraint on the problem is. Okay, let's just scroll down and track. Okay, so let's just look at another problem. So we'll be solving a couple of problems because like I think randomization can be best explained by solving like problems. This is not a topic in which has a lot of theory. So I'll just like show you one problem. Let me check. Okay, it is 10081. So so this is actually a problem from the ICPC Northeastern Europe regional contest. It's a very beautiful problem. Yeah. So let's just don't think it is very clear, right? Wait, let me just zoom in here. I think. Yeah, I think I should. Wait, let's just read. So we have this problem, and since some part was cropped out, it's okay. Queries are less than equals to n plus 500. Right. Let me just verify it. It's n plus 500, right? So you have to solve this problem. I'll give you some time to read this problem. And you have to solve this problem by using at most n plus 500 queries. So yeah, it's what time right now? It's 9:30. So I think we'll discuss by like try solving. We'll have a discussion at, let's give you like 10 minutes. Just like don't try to solve this, like your goal is not to solve this problem completely. Like even if I have an idea or a certain like direction towards which you can think, that would be like enough. Like I don't expect you to solve this problem entirely in 10 minutes, but if you have a idea or a direction in which to proceed, that's great. So I'll see you in 10 minutes. Okay, I think most of you should have at least tried by now. So I think we'll just start with discussion part for this problem. So let's just look at this problem. We have a function called one max, and like it takes our query string t, and like there's a hidden string s, and essentially what this one max does, like ignore all the jargon that's written in the statement. This one max calculates the bitwise and of s and t, and if number of set bits, if this is number of set bits in s and t, not actually number of set bits, number of matching bits, I should say. Number of matching bit at corresponding position, if they are n, then you win directly. If it is n by 2, it tells you that yeah, it's n by 2. Otherwise, it returns nothing. Otherwise, it returns 0. And you have to guess this string s within n plus 500 queries. Okay. So, and like, yeah, so this is like jump of one max actually. So, what what we can infer from this jump function is that any string which has like matching bits not equal to n or not equal to n by 2, that's basically like useless for us. We can't comprehend anything from that because interactor tells you nothing about that. We can only like if it is n, then we like straight up win. And another piece of info that we get from the interactor is if only if it is n by 2. So if we guess a string t which has n by 2 matching bits with s, then at the corresponding position as well, then tractor returns n by 2, and we are like, yeah, this is a string which has n by 2 bits set at the same positions, n by 2 same bits as t. So I'll just scroll down a little. Trackpad is having some issues today, I think. Can't seem to be So let's just, for the fact, like for the timing, let's just skip on how do we actually go about finding a t. Let's just say that you have already found some t which satisfies the above property that it has n by 2 bits, n by 2 bits which are similar at the corresponding positions. So now you have t. How do you go about finding s with this t? Like within as many few queries as possible, right? So let's just say my string t is t0, t1, t2. Well, let's just do one indexing, ignore this t0, tn. I have this string t which has n by 2 matching bits. So what I can do is like I can invert, let's say at ti here, I can invert ti and I can invert t1. And let's say if t1 is, let's say t1 and s1 are same and ti and si are same. Or let's say T1 and Ti both are correct, like as in both are equal to S1 or and Si. So in that case, our number of matching bits will go from n by 2 to n by 2 minus 2. Hence, we'll get a 0 from the interactor. Or one more case could be like if T1 is wrong, I mean T1 is not equal to S1 as well as Ti is not equal to Si. That means both are actually wrong in this T. So again, we'll go from n by 2 to n by 2 plus 2, and then again we'll get a 0 from interactor since it's not n by 2. And one more case could be that either of this is correct and the other guy is false. So in that case, we'll get n by 2 plus 1 minus 1, which is same as n by 2, so we'll get n by 2. So what we can infer from this query of 1 comma I, 1 comma I. Yeah. So basically by querying 1 comma I, we can see that if the correctness state, not the actual state of the bit, the correctness state of the bit, if they are both same, like either they are both correct or either they are both wrong, then the interactor returns 0. And if they are different, then if the correctness state is different, then the interactor returns n by 2. So like I'll just scroll down. Okay, okay. So now like for if we do this for every I, like within n queries, we can do this for every I. For every I, we can calculate whether Ti has same correctness state as T0 or not. Okay, and like we can maintain, let's say, two arrays. First array is, let's say, yes, which basically contains all the indexes that have same correctness state as T0. And we can maintain an array no, which has like different correctness state as T0. So we can maintain these two arrays, and like we have basically partitioned our all the bits of T into two segments, which is like yes and no with respect to T0. So if we fix like state of T0, if it is correct, then we can actually predetermine all the values of Ti, which could be like one possibility of S. If like let's say we assume that T0 is correct, then all the bits of T are already fixed, as we have already calculated the correctness state of all the I's. And we can also like assume that it is false, like T0 is not equal to S0. Sorry, T1, we are using one index, right? So we can like create two cases, either that T1 is correct or T1 is false, and correspondingly we can create two values of T and query both these values as like probable answer for this. Okay, I'll just scroll down again. So by doing this, like we spend n queries to determine the correctness state of every I, and then two queries to determine my probable answers. So we have used n plus 2 queries to determine S. But this thing we are only using that only using when we have determined T. The question still remains is how do we determine T? So let's say S is equals to some 100111001, some random binary number of length n. How do we determine a T which has, let's say, half the bits in like similar position? So basically, like out of these n bits, we want to choose exactly n by 2 bits which are same. So nc n by 2, and we want these to be same as corresponding bits in the S string as well. So we'll multiply 1 by 2 probability that uh, the random string t that we generate, the probability that half of these are same and half of these are not same. So what this expression basically is, we are choosing n by 2 bits from string t and fixing it to corresponding bits in string s with half probability for all these n by 2 bits, and the other half we want it to be exactly opposite to that of string s. So this is the probability that the random what do we say, the random string that we generate is like exactly has n by 2 set bits, and not set bits but n by 2 similar bits. Okay, so yeah, I think that's pretty much it. And yeah, like so we like got this expression right. MC n by 2, 1 by 2 to the power n by 2 and n by 2, that's basically 1 by 2 to the power n. So either you like intuitively you can see that the worst probability, like the maximum number of queries that we can take for getting such a string S, for getting such a string T is would be for n equal to 1000, which is our max n limit. So like you can use a scientific calculator to calculate this value for n equal to 1000, you'll get something like 0.025, I think. Or you can, if you don't have a scientific calculator, and or like you can also write a small script basically. Or if you want to just approximate using mathematical functions, then you can use uh, Stirling's approximation as well to approximate this value. So I'll just tell you what briefly this is. So by Stirling approximation, it is any number k factorial. This is root 2, approximately you can write it as a root 2 pi k by e to the power k. And like you can plug these values for this number. Basically plug this is nothing but n factorial, n by 2 factorial, n by 2 factorial into 2 to the power n, right? You can plug these values. You can approximate n factorial as well as n by 2 factorial by the Stirling approximation. And you can plug those values and then finally put in n to get 0.025 again. So basically, like the probability that you get such a string t, probability that you get such a string t which has n by 2 bits is same as s is 0.025. And number of turns, like let's denote this by p, and number of turns that we have, number of like queries that we have to perform to get such a string is like expected number of queries. Expected queries would be basically 1 by p, right? So this is 1 by 0.025, which is what, 40, right? Yeah, this is 40. So you get like 40 queries to perform, like expected number of queries that you have to perform to get a string t, which has n by 2 set bits, n by 2 similar bits as that of s is 40. And yeah, and like you can see, this is sort of like we are generating random t's until we get such a t which has exactly n by 2 similar bits. So you can see this, like our process, this is following this geometric distribution. And variance, like let's just calculate variance as well. Or let's just calculate standard deviation. Standard deviation for geometric distribution is 1 by p minus square root of this. And plug in those values, you get 0.025 by 0.025. Okay, let me just compute this value. Square root of 1 minus 0.025 divided by 0.05. Yeah, so this is close to 39. So with mean as 40 and variance as standard deviation as 39, like we are, and we use like how many queries? I think n queries, right? N plus 2, or yeah, something like n plus 2 queries earlier to get from t to s. And now with like close to 40 queries, 40 additional queries, and like standard deviation is 39. So like within n plus 40 queries, we can guess string t. And with like standard deviation is pretty much low, so you are almost like guaranteed to guess the string s within n plus 500 queries. So this is like a very like interesting problem. So like if you think like from a deterministic point of view, it is very complex. I am not sure like how would you go about solving that. But if you introduce randomness, this pretty much becomes very simple. Like you just have to like generate string t within like reasonable number of queries, and coming up with string s now that you have string t is like very easy. So this is like a very interesting problem, and it's also from like ICPC Northeastern European Regional Contest, I think 2015, if I'm not sure. Yeah. So yeah, it's problem from ICPC as well, and pretty interesting as well. Okay, someone has asked in chat, can rolling hash be used as a type of randomization problem? Rolling hash, yeah, rolling hash generates like basically it guarantees that the probability of your hash colliding is like very small. So it's a randomization process as well. Can't I do binary search for every fixed I within n log 29? I can reconstruct the entire array. We can get the max thereafter. Yeah, you can do that, but yeah, as I said before, that will exceed the number of queries. Like number of queries was n plus 2000, right? In the worst case, if you follow that process, you can take like n log AI query as well. Yeah, and I'll take like one more problem. So let's just start with this problem, right? So you are given an array of length n, and you have to find maximum such x such that x divides at least n by 2 numbers from your set. Numbers from this array. You have to find max such x such that x divides at least n by 2 numbers from this array. So like if your array looks like 3, 3, 4, 8, 4, then you would report 4, since 4 divides 3 elements and 3 is greater than equal to what is n? N is 5 by 2. Yeah. So you would report 3 in this case. And constraints on this problem is n is up to 1e6, AI is up to 1e12. And interesting thing to note is time limit is 4 seconds. And like what my solution does is like, and I've seen many other people's solution as well. My solution runs in like 3900 milliseconds, which is pretty close to time limit. And I think time limit is intentionally set very tight as per the constraint, because if you reduce the constraint, there are some other solutions that people can come up with, which I think they did not want. So yeah, if you want to solve, you can just pause the stream because I'll just start discussing this right away. Yeah. So if you need some time solving this, you can pause the stream because I'll be like starting the discussion right away. Right. So basically, what the problem is, you have to find a subset of this array such that its GCD is greater than 1, subset of array of length greater than equal to n by 2. So that is GCD is greater than 1 and its GCD is max over all such subsets. This is essentially what the problem is, right? So what can we do? So one approach could be like you can factor every number in the array and then check for every number, like if it is like how many number it divides within the array, and if it's greater than or equal to n by 2, you just report the maximum of all such numbers which follow this property. But that will take a lot of time. Like you need to factor all those numbers in the array. Then you will check like how many numbers it divides. So you will take n time for all such numbers. Like number of factors for a number ai is like close to ai to the power 1 by 3 for whatever limits we like, whatever constraint we generally have in competitive programming. You can use this approximation. So if ai is like 1e12, it is close to 1e4, like close to 1e4, not exactly 1e4. It is not bounded by 1e4, but it is in order of that. And I think the actual number is probably something like 6000. Like I checked when I was solving this problem. So I think that if I remember correctly, it is close to 6000 for 1e12. Like the maximum number of factors that a number can have up to 1e12 is 6000. Close to 6000. I'm not sure about the exact number. So yeah, I just scroll down. Yeah. So that approach is factually correct, but it will result in time exceeded. So what you can do is like whatever my answer x is x divides at least n by 2 numbers, right? Greater than or equal to n by 2 numbers, right? So x is a factor of at least n by 2 numbers. So if I choose like a certain amount of numbers, like let's just say 40 numbers per se. If I choose 14 random numbers from my array, the probability that x is a factor of at least one of them is like 1 minus 1 by 2 to the power 14. Right. This is the probability. Like if my number x is a factor of n by 2 elements, then the probability that if I choose 14 elements, 14 random elements from my set, from my array, then the probability that my number is a factor of at least one of them is 1 minus 1 by 2 to the power 14, which is very like close to 1. This is close to 1 as well. Like probably like this is something like 0.999. So pretty high probability that my my x is a factor of one of these numbers. So now you see what we have done. We have gone down from like finding factors of all the n numbers to finding factors of just 14 numbers. And with very high probability, we can say that, yeah, my x is a factor of at least one of these 14 numbers. So we have taken the advantage of this fact that x divides at least n by 2 numbers from my array. Right. So I'll just scroll. Yeah. So let's say we have a candidate list, some AI1, AI2, up till AI14. I have some candidate numbers whose one of the factors is x, right? So what I can do is for every number from this array, for every number of for every number in this array, I can like iterate over all my n values, and I can like calculate GCD of this number x. Like let's just say but the numbers are like, this is, let's say, the numbers are like, we can represent it by x. So we'll calculate GCD of x comma ai for every for all of the numbers. Like we'll calculate GCD of x comma ai for every I, and we'll maintain a we can maintain a map, or we can maintain a vector as well of size n to reduce time complexity. So we can maintain a map, and we'll increment this GCD x comma ai plus plus. Yeah. So for every x, I'm calculating GCD of x comma ai, and in the map, I'm incrementing its occurrence. Right. And since like I have to calculate such a number x, like I have to there exists there's like the problem guarantees that there exists a subset of length at least n by 2 which has a GCD g greater than 1, and we have to calculate max value of that GCD over all such subsets possible. So that's what I'm doing. I'm like calculating GCD of this x with AI, and like keeping a track of uh, counter of like this value GCD of x comma I for every n, for every I up till n. And I can do this, and what I can do is like scroll. Yeah. So now that we have this map, which basically stores the frequency of GCD of x comma ai, what I can do is like factorize x, and for every factor of x, and for every factor of x, I'll iterate on this map. This map has like this map stores pairs, which is number comma frequency. Number is basically this GCD that we have tracked, and its frequency in the array. And if my factor divides this number, then like I can keep a track of, like let's say I maintain a counter for every factor. Then I'll do counter plus equals frequency. So what I'm basically tracking is like for every factor of this number x, how many numbers it divides in the entire array. And if this counter is greater than equal to n by 2, I'll just update answer to max of, let's say, the answer that we have calculated up till now, and this factor f. So what we are doing is like we are basically guaranteed, like I just told. Oh, it's doing too much. Basically, we are essentially guaranteed ourselves that among those 14 numbers that we have randomly selected, at least one of them would have a factor, which is our actual answer. And for every factor of x that is in that is in those 40 numbers, for every factor of x, we are calculating like how many numbers it essentially divides in my array. So if we do that, we are essentially bound to get our answer. Like our approach is pretty much similar to that uh, unoptimal solution that we discussed earlier. So our approach is pretty much similar, but the fact that we have come down to only 14 elements instead of those n elements, we have pretty much sped up our process, and like the number of uh, like iterations that we are doing is very small. And like if you compute its time complexity, so like for every factor of x, we are doing this 14 times, and we are maintaining a map as well. You can use a hash map or I used a GP hash table to overcome the login factor. Like my solution was pretty much very boundary line, so I used a GP hash table. So that is O of one nearly, and I don't advise to use uh, hash maps or those things, but yeah, you can use it in some cases. And this thing you are iterating on factors and then factors of this again. So this is just divisor square, right? Yeah, because your map size is limited by divisors of x, right? Your map can only contain at most divisors of x elements. So divisors of x into divisors of x, and this will get pretty close to 4 seconds if you implement like this. But yeah, you can use pragmas and stuff, and try to use vectors instead of maps. Then you can pretty much pass in 3700 even. I optimized my solution from 3900 to 3700, I guess. Yeah, that's pretty much it. So the fact that we used random selection, like we randomly selected 14 elements only, that is our basically key to this solution. It's a very interesting problem, and I think it's rated around 2900 on Code Forces. So yeah, decent problem, and yeah, very interesting as well. Just see, I think that's pretty much it that we have to cover today. Right, I'll just see the chat if anyone has any doubt or anything. I don't see anyone. I have already answered. Yeah. Yeah, I think that's pretty much it for today. Yeah, and we'll share the uh, practice problems as well so you can solve. Thank you.